Consider the equation 2x plus y equals 5. This equation has two variables in it, x and y, and the truth of the equation depends on both of their values. So we can see that, for instance, if x equals 2 and y equals 1, the equation is true, since 2 times 2 plus 1 does in fact equal 5. On the other hand, if x is equal to 3 and y is equal to 0, the equation is false, since 2 times 3 plus 0 does not equal 5. So when we were looking at equations with more than one variable, we also have a notion of a solution to that equation. A solution to an equation involving more than one variable is not just a single number, but a pair of numbers. Because when you change the value of x, you might change whether or not your pair of numbers is a solution, and when you change the value of y, you might change whether the pair of numbers is a solution or not. So we say that a solution to an equation in the variables x and y is a point, is a pair, I should say, is a pair which we write using parentheses. I'll say it's a pair AB, where if x equals A and y equals B, the equation is true. Thus, in the example above, we would say that the pair 2, 1 is a solution. But we would say that the pair 3, 0 is not a solution. Notice that this is the same notation that we might use sometimes for interval notation, but the context of the problem means that confusion is almost never an issue. It should always be clear whether or not you're talking about a pair of numbers in the context of solutions to an equation, or an interval of numbers, such as we get in solutions to inequalities. So, this is what a solution to an equation is, and let's think about how we might find them. Let's look some more at this equation right here. So we've got 2x plus y equals 5. And we already know that the pair 2, 1 is a solution. In general, to find solutions to an equation, what we can do is just to plug in some number for one of the variables, then solve for the other one. Let's see how this works. And we often record the data of pairs of numbers that are solutions to an equation in a table where we'll record the x values on one column and the y values on the other. So we know that if x is 2 and y is 1, that is a solution to this equation. So in other words, the pair 2, 1 is a solution to this equation. Let's find some more. And the trick to this is that we can often plug in any number we like for either one of the variables. So, for instance, we could try saying, well, all right, what if x is equal to 0? If x is equal to 0, then our equation becomes 2 times 0 plus y equals 5. But now this is an equation in just one variable, and we know how to solve those. So 2 times 0 plus y equals 5 is equivalent to the equation 0 plus y equals 5, which is equivalent to y equals 5. So this tells us that if x equals 0 and y equals 5, we have a solution. So in other words, when x is 0, y is 5, as long as the equation holds. So that gives us another solution of 0, 5. We can also choose values for y. We could say, let's let y be 3. And if we do that, we get the equation 2x plus 3 equals 5. Subtract 3 from both sides to get 2x is equal to 2. Divide by 2, we get x equals 1. So this tells us that if y equals 3 and x equals 1, we have a solution. Now make sure that you keep the order correct. We are recording the values of x in the left-hand column and the values of y in the right-hand column. Now, what you see already is that we've got a lot more solutions to an equation like this than we did with equations involving just one variable. A linear equation with just one variable had one solution, or sometimes 0 solutions. Here we've come up with 3 already, and we could come up with a lot more just by choosing different values for x and for y, plugging them into the equation and seeing what else we get. So let's look at another example. So let's look at 3x plus y over 2 equals 7x minus 1. Now this is a pretty complicated equation right here, and plugging in a value for x or y and solving for the other one is a little bit of work. So what we often do, especially with complicated equations like this, is we can try solving for one of the variables. We can try to solve for either x or y. Often we solve for y because we're usually thinking of these equations as defining relations or defining functions, in which case we're usually thinking of x as the input and y as the output, and it usually makes more intuitive sense to solve for y than to solve for x, though that's not always necessary. So in this case, we could try solving for y, and once we do that, we'll be able to come up with a bunch of solutions to this equation a lot easier than just working with the original. So let's multiply 2 on both sides. We'll get 3x plus y is equal to 14x minus 2. We will subtract 3x from both sides to get y by itself, and we'll get y equals 11x minus 2. So this gives us an easier way to go from our x's to our y's. Now, if I want to come up with a table of solutions to this equation, I can pick a bunch of values of x. And so I'll pick, say, -1, 0, and 1. Again, these numbers are totally arbitrary. You could pick any numbers you like here for x or for y. But by doing it this way, we could work out the value of y easily because we've solved for it. So if x is -1, then y will be 11 times -1 minus 2, which is -11 minus 2, which is -13. If x is 0, then y is 11 times 0 minus 2, which is 0 minus 2, which is -2. And if x is 1, then y is 11 times 1 minus 2, which is 11 minus 2, which is 9. So this means that some solutions to this equation are -1, -13, 0, -2, and 1, 9. These are all solutions to this equation, but of course we can get a whole bunch more. We could get 2, 20. We could get 3, 31. We could, if we wanted to, get 10, 108. There are many, many solutions. In fact, if you look at this equation, y equals 11x minus 2, and think about it as a function, think about y as a function of x, we can see that the domain of that function would be all real numbers. You could plug any value in for x that you like and get a value of y out of it, a single value of y. Well, this means in particular that we have infinitely many solutions to this equation. This equation has infinitely many pairs because we could plug any number we want in for x and get a number and get a value for y out of it. But that's not the same as saying that all pairs are solutions. So some non-solutions would be the pair 0, 0. If I plug 0 in for x and y, then I don't get a true statement. I would get 0 equals -2, which is false. And you can come up with a whole bunch more non-solutions. In fact, if you just pick a random pair of numbers, it would probably not be a solution to this equation. But there are also infinitely many that are. So at this point, we run into the question of how do we represent the solution set to this equation? Because we can't describe it using a list of pairs the way that we could for equations with one variable. With one variable, there were a finite number of solutions to our equations, and so we could just write down what they were. But now we've got infinitely many solutions, and how do we represent them? The best way is going to be to represent these solutions graphically. It's going to be to describe all of these solutions, all the pairs of points that make this equation true using a graph. So let's talk about that, and let's talk about how we represent a pair of numbers, such as these solutions that we've got here, graphically. So for this, I'm going to give myself a grid to work with. Now, we are familiar with representing real numbers on the real number line. We can take the real number line and say, all right, that point's 0, there's 1, there's 2, 3, -1, -2, etc. And so we're able to represent a single number as a point on a line. We're going to represent a pair of numbers, two numbers, using a point in the plane. And we're going to do this in the following way. We're going to take a second real number line, and we're going to set it up at a right angle with the first one. So we're going to have one number line going vertically, one number line going horizontally, and meeting at the point where they're both 0. Now, the horizontal axis is usually called the x-axis because it's going to be used to represent the first number in our pair, which usually is represented by the symbol x. And the vertical axis is usually called the y-axis because it's usually representing the y values of the pairs that we're looking at. That is the second entries in it. So, a point x, y is, or I should say AB. actually, to be, in order to avoid confusion. A point A comma B, where A and B are both real numbers, is represented by the point sitting above or below A on the horizontal axis and to the left or right of B on the vertical axis. So let's see an example of what that means. Let's say I want to represent the point 2, the pair 2, 1. Well, I can do that on a rectangular coordinate system like this. As follows. What I do is I start by looking at the first coordinate, the 2, and I find that on the horizontal axis, the x-axis. And whatever point that I find is going to lie somewhere above or below that 2. And my second number is going to tell me where on that blue line my point sits by finding the point 1 on the vertical axis, the y-axis, and then drawing the line corresponding to that. So our point 2, 1 sits right here. It sits above the point 2 and to the right of the point 1 in the coordinate plane. Another way of thinking about this is that the coordinates of a point tell you how to get to that point starting from 0, 0. Now the point 0, 0 is very special to us. It's sort of the center of our whole system. And it has a special name. So the point 0, 0 here is called the origin. And so you'll often see questions or books refer to the origin, and it's always referring to the point 0, 0, which is where the two coordinate lines intersect, where the two axes intersect. And we can think of a pair of numbers, 2, 1, as describing a point that you reach by following a path where you travel to the right by 2. So you start off traveling horizontally, and the first number tells you how far you travel. And then you travel vertically by the number given in the second coordinate. So this point right here has coordinates 2, 1. Let's do some more examples. Let's think about this point right here. To find this point's coordinates, we can look straight up or down until we get to the horizontal axis, and straight left or right until we get to the vertical axis. And the numbers that we reach in each case tell us the coordinates of that point. So we see that this point lies above the coordinate 1 on the horizontal axis, and that means that its first coordinate is 1. Its x-coordinate, we say, is 1. Its y-coordinate, we see here, looks to be halfway between 2 and 3, and so that's going to be 2.5, but we write that as 5 halves, because improper fractions are much better to work with from an algebraic point of view. So let's do some more examples. What happens, we may ask, if we look at some negative numbers? So we look at -1, 2. Well, we still follow exactly the same strategy. We start with the first coordinate. The first coordinate is -1. And so we find -1 on the x-axis, and we look up or down from that. And we want to find the point on the vertical line at -1 that has a y coordinate of 2. So we're looking for something that has a height of 2, or in other words, is at the vertical level of 2, sits 2 units above the x-axis. And so that gives us this point right here is the point -1, 2. If we want to think about it in terms of how we travel to get there, then a negative value here means we travel to the left if the x-coordinate is negative. So a -1 means that if we start at the origin, we move to the left by 1, and then we look at the y-coordinate. In this case, the y-coordinate is +2, so we'll move up. But if the y-coordinate, the second coordinate, is negative, we travel down. If the y-coordinate is negative. All right, one more example here. Let's look at -2, -3. Well, this point has negative x-coordinate and negative y-coordinate. So, to get to -2, -3, I would start at the origin and move to the left by 2. I move to the left by 2 because that's what the first coordinate's telling me. And the first coordinate always tells you the horizontal movement from the origin. And then the second coordinate, the -3, tells me that I'm going to move down by 3. And so this point right here is the point -2, -3. Now, it's very important to remember that the coordinates of a point have an order that matters. The first coordinate is always telling you about the horizontal position of your point. The second coordinate is always telling you about the vertical position of your point. And if you switch the order of those two, you get something different. So for instance, we've got this point -1, 2 up here in the upper left part of the graph. But if we were to change the order of those points, we would get the point 2, -1. And that will give us a point where we move right by 2 and down by 1, so it would give us the point down here. So we get the point 2, -1 right there. So the order very much matters. Notice that the points -1, 2 and 2, -1 are very far away from each other. And so changing the order of the points changes, the order of the coordinates rather, changes the point that you're looking at there. Now, a last piece of terminology that we have for the rectangular coordinate system is as follows. We will often describe the 4 quarters of the plane that are defined using these axes in terms of quadrants. So the upper left quarter of the plane, the one that consists of all the points with positive x-coordinate and positive y-coordinate, sitting to the right of the vertical axis and above the horizontal axis, is called Quadrant 1. We then name the quadrants in order going counterclockwise around the graph. So the upper left quadrant is called Quadrant 2. The lower left quadrant is called Quadrant 3. And the lower right quadrant is called Quadrant 4. And we can look at each of these quadrants and identify them, as I just said, in terms of whether their x-coordinates are positive or negative. Quadrant 1 consists of all the points where the x-coordinate is positive and the y-coordinate is positive. Quadrant 2 consists of points that lie to the left of the vertical axis. Being to the left of the vertical axis means that your x-coordinates will be negative, because a negative x-coordinate means that we're starting our process by moving to the left, and that's going to put us over there in Quadrant 2, and then this gives us positive y values because all these points lie above the x-axis, so they all have positive y-coordinates. Moving on to Quadrant 3. Quadrant 3 has negative x-coordinates and negative y-coordinates. Quadrant 4 has positive x-coordinates and negative y-coordinates. So for each combination of positive or negative that you can associate with the x-coordinates or the y-coordinates of a point, that will give you one of these four quadrants. So it turns out that this coordinate system, the rectangular coordinate system, is perfect for describing solutions to equations with two variables, because we can take each one of the points that are solutions to that equation and represent them by a point on the graph. So let's see how we'll do that with an example. So to graph the solutions to an equation, we're going to have a couple of different strategies here, but our basic strategy is going to be the following, and we'll be able to refine this in specific situations. To graph the solutions to an equation, we want to find a sufficient number of solutions, graph them, and then connect the points. Let's see how that goes with a specific example. Let's say we want to graph the solutions, graph the solution set of the equation y equals 3x, sorry, I want 2x minus 1. So one of the things we can do is to follow this strategy. Find some solutions, plot them on the rectangular coordinate system, and then connect them up. Let's see how that goes. You'll notice that in my first step, I use the phrase find a sufficient number of solutions. That is intentionally vague because depending on how complicated your equation is, you're going to need more points. It turns out that for this equation and for others of its kind, we only technically need 2 points, but in order to justify why we do that, we're going to take about 5 for this one here in this example. So let's get some solutions to this equation. And I'm going to take the following numbers for my x values. A lot of times when you're graphing points, it's helpful to choose numbers that are close to 0. That helps to graph it out. So we'll take x to be 2, -1, 0, 1, and 2. And then y, in each of these cases, we can figure out. So if x is -2, y is 2 times -2 minus 1. Whoops, that looks like a plus, minus 1, which is -5. So that means that the point -2 comma -5 is a solution to this equation. And we get y equals 2 times -1 minus 1, which is -3. So we get -1 comma -3. We get y equals 2 times 0 minus 1 is -1. So we get 0 comma -1. Y equals 2 times 1 minus 1, which is 1. So we get the point 1 comma 1 as a solution. And y equals 2 times 2 minus 1 is 3. So we get the point 2 comma 3 as a solution. So we've got a collection of 5 solutions here. Let's go ahead and try to graph them out. Now, once you have your solutions, you can set up your graph and try to be strategic about it to give yourself enough room to graph these things. Notice in particular, I see that my y values are going down to -5 and up to 3, which means to graph this out, I'm going to want to include vertical coordinates at least up to 3 and down to at least -5. And often it's helpful to go even a little below that. So -1, -2, -3, -4, -5, -6, -7. Now, generally speaking, you want to use the same scale on both of your axes. So here I'm using a single tick mark to mean 1 unit, whereas before I was using 2 tick mark, 2 of my squares on my grid to stand for 1 unit. Here, because I'm using 1 square for 1 unit on my vertical axis, I'll go ahead and do the same on my horizontal axis. Now, this isn't strictly necessary, and if you happen to be working a problem where the types of numbers you're working with, where the scale of the numbers you're working with on the x side and the y side are very, very different from one another, then it can make sense to use a different scale for one axis than the other. Also, depending on your situation, you may only include one quadrant of the graph. It's very common to see graphs which only include the positive x and positive y axes and happen entirely in quadrant 1. This is because many graphs are studying quantities which don't make sense if they're negative. So there are lots of variations that we can see of the coordinate system, but this is the basic part. So let's graph out our points. We've got -2, -5. So I'm going to go over to -2, and so let me sketch out what my thought process is as I do this. I start at the origin, I go left to -2, and then I'll go down until I get to -5. And that tells me that this point here is the point -2, -5. When you are graphing out these problems, it's often a good idea to label your points. In fact, you usually should. All right, our next solution is -1, -3, which we represent by going over to -1, going down to -3. 0, -1 will appear here. So an x coordinate of 0 means we actually don't move at all. It means that we're actually staying on the vertical axis, not moving left or right, but just up and down. So we get the point 0, comma, -1. Oh, I forgot to label my other point. All right, now the point 1, 1, we'll get that by moving to the right 1 and up 1. So we've got this point which sits above 1 on the vertical axis and to the right of 1 on the, above 1 on the horizontal axis, to the right of 1 on the vertical axis. And then finally, 2, comma 3. We'll go over to 2, go up to 3, and get this point 2, comma 3. So this gives us 5 points that represent the solutions to the equation. I want to emphasize that a solution to an equation is a pair of numbers. And the rectangular coordinate system allows us to represent pairs of numbers as points, as geometric points in the plane. But the solution is still the ordered pair, not the point, not the physical point itself, but just what it represents. We're often a little bit loose when we talk about that, and I probably will be also. But let's try to be precise here, at least to begin with. All right, now this gives us 5 solutions to the equation. But of course, as we discussed before, there are actually infinitely many solutions to this equation. What you may notice about all these points, however, is that they aren't just randomly scattered around the plane. In fact, they all seem to line up. They seem to lie on, in fact, a single line which goes through all 5 of those points. And in fact, that blue line continued on forever in both directions, is the solution set to this equation. So this blue line right here is the solution set. Now, this means a couple of things. To say that this line is the solution set or contains all the points corresponding to the solutions in the of the equation means 2 things. It means that every point on the line is a solution to the equation. That's part of what saying it's a solution set means. Also, it means that every solution to the equation corresponds to a point that lies on this line. So in other words, the points that correspond to solutions of this equation are all of the points on this blue line and nothing else. Proving the second part is a little bit tricky, but we can justify to ourselves that the first part is true, that we can take an example here to try and convince ourselves that every point on this line is in fact a solution to the equation, even the ones that we didn't write down. This green point here looks to be approximately 1.5, looks to be sitting approximately over 1.5 on the x-axis, which we will write as 3/2, and it's sitting to the right of the number 2 on the vertical axis. So this point has coordinates 3/2, 2. It corresponds to the pair 3/2, 2. If what we're saying is correct, that the blue line is the solution set to this equation, then if we plug 3/2 in for x and 2 in for y, we should get a true statement. Let's check. So here we're doing a check. If we take 2 equals 2 times 3/2 minus 1, let's see if this equation is true. That gives us 2 equals, now 2 times 3 halves is actually 2 over 1 times 3 halves, which means we get cancellation of these 2's right here. Canceling the 2's gives us 3 minus 1. So 2 times 3 halves is 3. So we get the equation 2 equals 3 minus 1, which checks out. So that tells us that this green point right here is a solution to the original equation we looked at. And we can do the same thing with any point along this blue line. We can take the point, find the ordered pair of its coordinates, and check that the equation is satisfied when we plug in those numbers to the equation. Now, the thing that made this work, that we just got a line as our solution set, is that we were dealing with a linear equation. And so this is really where the justification for the definition comes in. We talked about linear equations way back at the beginning of the course. I said that we'd see why they have that name later. This is why. Linear equations are equations whose solution is a line, whose solution set, rather, is a line. So let's look at the fact that we're going to use very often to go and graph lines. So, fact, if A equals B is a linear equation, in x and y, meaning it uses the variables x and y, then its solution set corresponds to a line in the rectangular coordinate plane. Now, one of the things this means is that we don't have to graph 5 points when we're looking at a linear equation. And this is because we know from geometry that a line is determined by exactly 2 points. If I just know 2 points on a plane, there's only one line that goes through them. So what this means is that to graph a linear equation, which means to graph the solution set of the linear equation. To graph a linear equation, we just need to find 2 solutions, plot those points, then draw the line through them. So 2 points is enough to sketch the graph of a linear equation. Now, it's usually a good idea to go ahead and plot 3 just as a way to check your work. But we really only need 2 of them. So let's see how we do this with another equation. So let's graph the equation 2x plus y equals 5, the equation that we had last time. So we can get our equations from anywhere that we like. Or, I'm sorry, we can get our solutions any way that we like. In particular, we can choose any numbers to plug in for x or for y. So let's do a couple of the ones that we did before. So if x equals 2, that means we get 2 times 2 plus y equals 5. So 4 plus y equals 5. subtract 4 from both sides, we get y equals 1. So this means that 2 comma 1 is a solution. We found that by choosing some value for one of the variables and solving for the other one, which is a very good way of finding solutions. And then if y equals 3, then we had that 2 times 2x plus 3 equals 5. So 2x equals 2 after we subtract 3 from both sides. And we got x equals 1. So this means that the point 1 comma 3 is a solution. All right, so let's graph this out. I'm going to do a fairly small graph for this one. We've got 2 solutions, and that's good enough. That's all we're going to need. So we have that the point 2 comma 1 is a solution. That point is right here. It has an x-coordinate of 2 because it lies above the 2 on the x-axis. And it has a y-coordinate of 1 because it lies to the right of 1 on the y-axis. So there's one of our solutions. We also have that the point 1 comma 3 is a solution. So there's our other one. We now have 2 points in the plane, and therefore there's only one line that goes through both of them. And that line is the solution set to this equation. So this blue line is the solution set. Or in other words, it's the graph of 2x plus y equals 5. It's the set of all points with coordinates that are solutions to the equation 2x plus y equals 5. All right, so let's look at a couple of pieces of terminology related to graphing linear equations, and look at one strategy that we can use for graphing them that's pretty simple, that's often pretty simple. All right, so this form of a linear equation that we have right here is one that comes up a lot in applications, so much that we have a name for it. A linear equation in the form ax plus by equals c, where a, b, c are constants, is said to be in general form. Sometimes a problem will ask you to rewrite an equation in general form, and I apologize. General form is not the term that our book uses. Our book uses standard form. Sorry about that. So we will say that this equation is in standard form. Now, an equation, the equivalent equations can be in standard form and look a little bit different. Now, so for example, if we looked at the equation x plus y equals 6, and the equation 2x plus 2y equals 12, so these two equations are both in standard form, and they are equivalent. Notice that I've just gotten one from the other by multiplying everything by 2. So in fact, they're going to have the same solution set. They're both in standard form, and so that's fine. We don't make any bigger a deal out of it than that. Okay, so for another example of a problem that we might run into, we might say write the equation 2 times x minus 3 plus 6 equals 1/2 times x plus 2y in standard form. Now, to put it into standard form means to make it look like this. So what you're going to want to do is expand everything out, gather all the x's and y's on the left side of the equation and all the constants on the right side. Once you do that, then you're going to have standard form. So let's do that here. If we distribute everything here, we'll get 2x minus 6 plus 6 after we distribute the 2 through. And distributing the 1/2 through, we get 1/2 x plus 1/2 times 2y. Now 1/2 times 2 is just 1, so those two cancel. And also we've got -6 and 6 that cancel, which gives us something convenient. So we get 2x is equal to 1/2 x plus y. So to get standard form, we'll subtract 1/2 x from both sides. And we'll also subtract y from both sides because we want to get all the x's and y's on the left. Now 2 minus 1/2 is 3/2. So 3/2 x minus y equals 0, and there's our answer. If we still had any constants left over on the left-hand side, we would need to move them to the right-hand side in order to put this equation in standard form. All right, so last thing for right now, there is a pretty simple way of graphing equations, especially when they start off in standard form, and that's by finding their intercepts. So we need a bit of terminology here. The x-intercept of a graph, or I should say an x-intercept of a graph, is a point on the graph which lies on the x-axis, the horizontal axis. A y-intercept of a graph is a point on the graph which lies on the y-axis. So just sketching out a sort of arbitrary cartoon graph. If, let's say I have some linear equation whose graph looks like this. Well, then I can find the places on the graph where the graph intersects the x-axis or the y-axis. So this point right here is going to be the x-intercept. And the thing to note about the x-intercept is that no matter what the x-coordinate of this point is, it's always going to have a y-intercept, a y-coordinate rather, of 0. And that's because every point on the x-axis has a y-coordinate of 0. Every point on the x-axis has coordinates of the form something, comma, 0. Similarly, every point on the y-axis has coordinates of the form 0, comma something. So this gives us a strategy to find the x-intercept of a graph. We want to set y equal to 0. So to find the x-intercept, we set y equal to 0 because every point on the x-axis has a y-coordinate of 0. To find the y-intercept, set x equal to 0 because all of the points on the y-axis have an x-coordinate of 0. And the nice thing is, when we're dealing with linear equations, that gives us 2 points usually. And so once we have those 2 points, that's good enough to graph the line that we're looking at. So let's see how that goes. And as I said, this technique is particularly useful when you've got equations in standard form. So let's graph the equation 2x plus 3y equals 12 by finding its intercepts, that is, its x and y intercepts. So let's do that. So to find the x-intercept, we set y equal to 0. So that'll give us the equation 2x plus 3 times 0 equals 12, which gives us 2x equals 12. Dividing by 2 gives us x equals 6. Now, the x-intercept is, properly speaking, not 6, but the point 6, comma 0. So the x-intercept is the point 6, comma 0. Now for the y-intercept, we're going to set x equal to 0. So we'll get 2 times 0 plus 3y equals 12. So 3y equals 12, because we get 2 times 0. Dividing both sides by 3, we get y equals 4. So that tells us that the y-intercept is 0, comma 4. Note in the first case we set y equal to 0 and got x equals 6. So our point that we found was 6, comma 0. Our y-intercept, we set x equal to 0 and found y was equal to 4. So our point on the y-axis is 0, comma 4. Notice that this is exactly the same process we used at the beginning of the day. We're just plugging in specific values in order to get the intercepts that we're looking for. So now let's graph this. And let's see, we're going to need 1, 2, 3, 4, 5, 6. And I always like to go one more. So we've got the point 6, comma 0 on the graph. And then we've got the point 1, 2, 3, 4. We have the point 0, comma 4 on the graph. And then the line will, oh, whoops, did I? Oh, I got it. Yep, there we go. And so the graph of our solution will go through those 2 points. So here's our solution set. Is this line. So that's how we can graph equations by finding the intercepts. which is especially useful when they start off in standard form, because as you saw, the process for finding the intercepts was very easy, because in each case, one of our terms just turned into 0, and we were left with a very simple 2x equals 12 or 3y equals 12.